Hey everyone, and welcome back to my channel. I'm Anish, and today we are going to learn a very good concept of Bode plots. Basically, someone from on one of my old videos commented about infinite gain on like realizing poles and zeros of Bode plot. I will put that video link on the description or in the pinned comments. So from there, like I was going to put this video out previous year, but then a lot of things came up, so I forgot to put this video out about Bode plots in 3 dimensions. So today I'm going to explain about Bode plots in 3 dimension, and actually what does Bode plots mean and what parameter do we vary in the Bode plot. That is very important. Okay, so like in front of you a very simple question is given that you have to plot the Bode magnitude plot for the following circuit, simple series RL circuit. I've already done this multiple times. Okay, like again I will do it. Like this is just a simple cakewalk for you if you have watched my channel. Then we also have to find the frequency at which we can have infinite gain. Okay, we have to find the frequency at which we can have infinite gain in this circuit. So let's just plot the Bode plot. So for plotting the Bode plot, we have to find the poles and zeros of this circuit. So like you can either do it with the transfer function method, convert this in the Laplace domain, and then you directly solve with v over vi of s, or you can find the poles and zeros intuitively. So how to find the zeros intuitively? What you can do, like there are two methods. Either you can break the link, okay, or you can short the output. So here, can we break the link? No, we can't, because this r is a constant value. We can't change anything, so we can't break the link. Okay, can you short the output? Yes, at s equals to 0, this is going to 0, so we can short the output like at s equals to 0. So obviously we have a 0 at s equals to 0, 0 at s equals to 0. So this is the first thing. We have a 0 at s equals to 0. Now if you have a 0 at s equals to 0, then dc gain is 0, so that thing is gone. So with dc gain we used to find the value of a, but now we couldn't. So we have to make other arrangements. So we'll see about that later. So next is we have to find the poles. So poles is either like inverse of the time constant, negative inverse of the time constant, or simply you see infinite impedance from here. So what you can do is you can break this, like you can short the input and you see infinite impedance from the output node, right? Output port. So how to make this infinite impedance? So basically what you do, we know that if there is some two impedances here, if this is the negative of this, then this will become infinite impedance, as these are in the parallel. All this I have explained in that realizing poles and zeros intuitively. So I'll put that video link in the comments below. So now basically this has to be r equals to minus sl. So s p will be equals to minus r by l. So I have a pole, single pole at r by l. Because this is a first order circuit, I will have only one pole. So yeah, I got the 0, I got the pole, so I can write the transfer function in this format. A s by omega p. So s by omega p it should be, so it should be s by r by l, which will become l by r plus 1. Okay, so yeah, now how to find the value of a basically. So how to find the value of a? So what you can do is find the high frequency gain. So at high frequency, what is happening? At high frequency, this is giving me infinite impedance. Okay, hence no current will flow through here, and these two are in series, hence no current is flowing through here. So drop through this is 0, hence vi will directly come across the output. So my high frequency gain is what? Vo equals to vi. So ho at s equals to infinity, vo equals to vi, hence vo by vi equals to 1, which is equals to h of infinity. So if I put s equals to infinity over here, then this should tend to 1. So if I put s equals to infinity, what will happen? The coefficient of only the s terms will remain. So a by l by r, equals to 1. I'm like sorry if some noise is coming from outside. So yeah, someone is like talking very loudly like in front of my this door. So a by l by r, and this a equals to l by r. Okay, so a is equals to l by r. So I can write the equivalent transfer function like this, that my h of s equals to l by rs divided by S L by R plus 1. Okay, so next I told you to plot the Bode plot. So how do we plot the Bode plot for this? So what do you observe is we have a 0 initially. We have a 0 at s equals to 0. So we have a 0 initially. So our initial slope of the Bode plot will be plus 20 dB per decade. Like this, how to plot the Bode plot, all these things I have done a video in my channel, or I have in my comprehensive control systems course. There I have explained everything from the basics. Like that hasn't been uploaded yet. That will be uploaded soon. So I will just put the link in the comments below after it gets uploaded. Okay, so yeah, we will get it. I will not explain anything here. I will just directly draw the Bode plot because it is not possible for me to explain. So we'll, like, if I have a 0 at s equal to 0, I will get a plus 20 dB per decade slope initially. So my Bode plot will look something like this. This is omega, but remember, this is not in decimal scale, this is in decade scale. Okay, so many people get confused with this. All this I have explained in my comprehensive course, decade scale. Okay, and here in the y-axis, what do we plot? We plot the magnitude. Like, I'm only concerned with the Bode magnitude plot. So magnitude of h of j omega in dBs, okay, and this is in radian per second. Okay, so what is actually happening here is my initial slope is plus 20 per decade, but if I put here s equals to 0, what will happen? Like, can I, like, obviously in Bode plots also we don't plot for the frequency s equal to 0, we just plot s equal to 0 plus something just more than s equal to 0. Okay, because log of 0 we don't plot. That is the reason. So now like here, if I put s equal to 0 over here, what do you get? We get gain 0. So obviously, can you get, like, what is the log of 0? Log of 0 is minus infinity, right? Here also log of 0 is minus infinity. That is why we don't plot omega equals 0. Log of 0 is minus infinity, so we won't be able to obviously plot that here. We will just assume that it is coming from minus infinity to some value. Okay, and the slope is plus 20 per decade. Okay, so here the slope is plus 20 per decade. Then at corner frequency, what is the corner frequency? The corner frequency is this, right? The pole. So omega c equals to r by l. So this is my corner frequency, but this is like where I get a pole. So here my slope becomes what? This gives a slope of minus 20 per decade, and this is already giving me plus 20 per decade. Overall my slope will become 0 dBs per decade, plus 20 dB and minus 20 dB. So this will be 0 dBs per decade. And what will be the gain here over here? So the gain over here will be something. Okay, so I don't know, so you just derive whatever will be the gain, you can derive it for yourself. This will be r by l. Okay, and this will be some gain k. Okay, just put the value of r by l here and you'll see whatever the gain is. So this is how we plot the Bode gain plot for this particular circuit. Very simple, nothing fancy here. But what next we have to find out is, we have to find out the frequency at which we have infinite gain. So here, what do we have to do? Wait a second, what do we have to do? Basically, hold on a second, we have to make this infinite gain. So for us to make this infinite gain, this denominator needs to go to 0. That is the main thing, right? Poles, what does definition of pole mean? The definition of pole means when the denominator goes to 0. So here, if I make the denominator go to 0, this will be s l by r plus 1 equals to 0. Now s equals to minus l by r, and at this frequency I will get sorry, not l by r, sorry, r by l, and at this value of frequency I will get infinite magnitude. Now few people get confused with this. They assume that this is this frequency r by l. They assume this is this frequency, and they assume like this is telling me that at this frequency I will get like infinite gain, but in the Bode plot it is not telling that. It is telling me that I will get some finite gain. Then what went wrong here? What is the problem here? The problem is this s equals to minus r by l is different, and this r by l is different. So what is this r by l? This r by l is simply omega equals to r by l. Okay, and this r by l is s equals to minus r by l, which is different. So so what I will come to is the definition of complex frequency here. So I will explain about complex frequency, then I will come back to this thing. So here, like I've explained in my full course in control systems, I will put that link in the description, like in the comment section below, that what is complex frequency. If you want to know more about complex frequency, I'm just giving you the brief definition of complex frequency. So what is a complex frequency? A type of frequency that depends on two parameters. One is the sigma, which controls the magnitude of the signal, and other one is the omega, which controls the rotation of the signal. Is known as complex frequency. So like you already know this, I think by now, that S equals to sigma plus j omega, which we call as complex frequency. Okay, like why is this important? Just as complex number is important, because or like we use complex numbers to mathematically derive few things, to mathematically model. So this complex frequency is also used in that case, that to mathematically model few things. Just take the example of an inductor capacitor. We mathematically model those circuits with the help of complex numbers, right? Complex frequency, all those things. So here also the same thing. Like don't ask me what is the physical significance of all this. So they are important to mathematically model all electrical components and other things also, like in other branches, engineering branches also. So this is the first thing. So S is defined as sigma plus j omega, where sigma is the like real part of the complex frequency, and omega is the complex imaginary part of the complex frequency. Okay, so this is my S equal to sigma plus j omega. And in Bode plot, what do you do? In Bode plot, basically if I just draw the S plane, sigma and j omega, if I just draw the S plane, what do we see is that we are only plotting for positive frequency. What do you mean by positive frequency? This part, from 0 plus to infinity, omega equals to 0 plus to infinity. Okay, we're not concerned with this sigma. Like sigma is 0 in this case, sigma is 0. Okay, so that's why we don't like see all these things. So sigma is 0. So in when we are plotting for Bode plots, this axis, right, in this axis this is the omega axis. Remember, this is the omega axis, and omega is varying from 0 plus to infinity. Okay, so that is why in our Bode 2D plot we don't see anything blowing up, we don't see anything going to infinity. Okay, so what is this then? What is this? This is the real part of the complex frequency. So at sigma equals to minus r by L, and omega is 0 in this case, and omega 0, this will go to infinity. This will go to infinity. Okay, if you want to further like deep dive into this, like further go into this, what, like how we can break this down S into. So we can break this down, transfer function S equals to sigma plus j omega, right? Sigma plus j omega. Now what I can write, this is sigma plus j omega into L by R, and in the denominator this is sigma. I have broken this down plus 1. I'm just making the real and imaginary terms, collecting the real and imaginary terms separately. So now I will just calculate the magnitude. So the magnitude will be sigma square plus omega square under root into L by R divided by sigma L by R plus 1 whole square plus omega square under root. Okay, so here what is important? The important part is for this to go to infinity, this has to individually go to infinity, this has to this has to individually go to 0, and this has to individually go to 0, because they are sum of two squares, and you know, like the minimum value of this is 0, and when individually these two are 0, then only we will get the minimum value. So obviously I need the denominator to go to 0 for this whole magnitude transfer function to blow up to infinity. Okay, so just mind excuse my handwriting for now. So yeah, here, like from here also I have proved the same condition which I wrote here, if you get confused. So yeah, this is the first thing, So in Bode plot we won't be able to see this, but I'll show you in 3D Bode plot how we see, like, get infinite magnitude. So this is the first thing. Now the next thing is I have another question. same thing only. We have to plot the Bode magnitude plot for the following transfer function. Here the transfer function is bit changed now. Like my poles are not distinct anymore, they are not real anymore, they are complex poles. So if you just find the poles here, just simply use Sridharacharya formula. This will be minus 2 plus minus v square 4 minus 20 by 2a, which is minus 1 plus minus, just hold on a second, let me just make my handwriting bit better, j4. Okay, so here these are complex pole. Now in Bode gain plot, what we do is we approximate this. How do we approximate this? Like obviously there is no time for me to like explain here fully, but what we do is, this is a standard second order system, zeta based standard second order system. So what we assume is that there are two poles at omega n. So what is the omega n of this? So if we compare this with standard second order system, which is s square plus 2 zeta omega ns plus omega n square. Now omega n in this case will be under root 5. So Bode plot is a approximate plot. It is a asymptotic approximate plot. It is not an exact plot. Okay, so obviously we approximate few things. So while the definition of this Bode plot, doing the definition for second order systems or where my poles are complex conjugate poles, what we say is, we say that I have a corner frequency at omega equals to omega under root 5. Instead of this pole, I have a corner frequency at omega equals to omega under root 5. So omega is under root 5, and I have two poles at that frequency. So two poles at this frequency. Under root 5. So yeah, this is the first thing. Now if I have two poles at this frequency, what will be the slope of my Bode gain plot in this region? The slope will be minus 40 dB per decade, right? The slope will be minus 40 dB per decade. So just look, I should have written the slope here also. I forgot to write the slope. Slope here is plus 20 dB per decade. Then I get a pole, so the slope becomes minus 0 dB per decade. Okay, so this is the first thing. And what other thing do we notice? We notice that yeah, this will give me slope of minus 40 dB per decade. That is fine, but I have a 0 first. I have a 0 at s equals to 0 and not a 0, sorry, two zeros at s equals to 0. So how much slope will this contribute? This will contribute me 40 plus 40 dB per decade. So initially I will have a slope of plus 40 dB per decade coming from minus infinity, because as you know, DC gain of this is what? DC gain is again 0. So it is coming from minus infinity. Gain is, like if you do log of 0, it is minus infinity. So DC gain of this is infinity. So this will look like almost similar to this, but there will be difference. What will be difference? I will just tell you in a second. Just let me copy this first. If we draw the Bode approximate plot, almost same, this will be almost same. The difference will be in this slope. The slope here will be 40 dB per decade, and I will have a corner frequency at what? Under root 5. Under root 5 I will have a corner frequency, and obviously I told you, right, after this corner frequency it will contribute minus 40 dB per decade, and obviously initially I had plus 40 dB per decade. So overall my slope again will become 0 dB per decade, which is again correct. Why? Because if I do s equals to infinity here, I get a constant gain. Which is 1. Okay, one thing I made a mistake over here. Okay, this will not be actual k. At infinite frequency my gain will be 1. In dBs it will be 0. So here obviously I can directly make this 0 dB. Okay, 0 dBs. Okay, either you can bring down this axis, that doesn't matter, you just write here 0 dBs, that is also fine. So this is 0 dBs. Why? Because you put s equals to infinity over here. Like just with the circuit we can understand, right? S equals to infinity, what is happening? Vi equals to Vo. So that is what how we got this a value, right? So s equals to infinity, this will be 0 dBs. I got confused earlier, so yeah, sorry for that. So here also at s equals to infinity, only the highest power coefficient terms will remain. So here 1 by 1, which is again 0. So log of 1 is 0. So this will again be 0 dBs. So this is one thing. Okay, now what will be the actual plot. Like in Bode plot, what is happening, we are approximating here very badly. Like I've explained in my full course, like this is a very bad approximation. Basically there is huge error here, but still like we do it because we just want to plot the approximate plot very easily. So I have plotted this in the MATLAB, and if you see here, like this is the approximate plot, and this is the almost the like magnitude plot, almost exact plot here. So if you see here, these are almost similar. Okay, and in the MATLAB I have plotted this exact same transfer function. And if you observe few things, that if you want to cross check, right, the assumption that we took, that it is plus 40 dB per decade, is it true or not true? So here initially there is a, no sorry, not this assumption, this one, but for like here what do you see, there is some slope, and this part has zero slope. So obviously whatever slope we had here, this is totally getting cancelled here. So is this like what is the slope here then, if I find the slope here, then we can find how much slope this part is contributing, so that it is getting cancelled. Basically what I want to say you is that the assumption that we took, that yes, I am getting two poles here and my slope is becoming, this is contributing minus 40 dB per decade, is this true or not? How, like, is this a good approximation or not? So how much slope is this? Basically just remember, this is in log scale. Okay, this is not in radian per second, like this is written wrong here, this is not in radian per second, this is in log scale. So here -1 is not omega equals to -1, it is 10 raised to power -1. So 10 raised to power -1 is basically 0.1. Okay, and here 10 raised to power 0 is 1, and 10 raised to power 1 is 10. Okay, this is in log scale, this is in decade scale simply. So here if I observe one thing, this is, let's say, somewhere less than something less than -50. Okay, and if I travel one decade, how much is my magnitude increasing in dBs? So in dBs I am something lower than -10. So I am totally traveling how much? Almost 40 dBs. So this distance is almost 40 dBs. So in 1 dB I'm traveling, in 1 decade I'm traveling 40 dBs. So again, this is correct, right? This is correct, because if I'm like, this slope is then plus 40 dB per decade, and here my slope becomes almost 0, because this is a flat line, constant line, 0 dB per decade. That means this after this portion, this is contributing minus 40 dB per decade, and overall my slope is becoming 0 dB per decade. So our approximation is correct, that the Bode magnitude plot should give a minus 40 dB per decade after this corner frequency under root 5. So that is the first thing, that is why we do the approximation. So next is our corner frequency correct? So here, almost here, the frequency is changing. So if I just bring this point down almost here, this is almost like this scale is linear, but in log scale this is almost like 0.375. okay, 0.375, but this is in log scale. So if I want to get the actual frequency value, this will be 10 raised to power 0.375, which will be almost, like I've already calculated it, it will be almost equals to under root 5, which is the assumption that we do. Okay, almost equals to under root 5. So yeah, that is the thing about the Bode magnitude plot. But the thing for which all of you came for, the 3D Bode magnitude plot. So here, can you see me, where does my magnitude goes to infinity? The magnitude will go to infinity at poles. So what are the poles at these frequencies? These are the frequencies at poles. So here, what does this represent? This, like, these poles represent where my magnitude or this transfer function goes to infinity. So here -1 represents the sigma value, sigma equals to -1, and omega equals to ±4. Obviously we don't talk about negative frequencies, but like in signals and systems, all there for mathematical approaches we talk, but in real life systems we don't talk about negative frequencies. So at these two particular frequencies, it will go to infinity, magnitude will go to infinity. So here is the 3D magnitude plot. Okay, here you see that my sigma is, like, I'm going from positive, like 0 to negative sigma, negative values of sigma, and omega is here it is 0 and it is increasing in this area. Okay, so yeah, sorry, like, where is, like, omega is 0 here, sorry, omega is 0 here. Okay, omega is 0 here. Yeah, omega is 0 here, and it is increasing in this region. So here what we see is if I go minus one step here, and then if I increase here, okay, if I increase slightly, so at what omega goes to 4, this is blowing up, this is blowing up. Okay, more prominently you can see here, like obviously we can't plot it, right? We can't plot it because like it is going to infinity, so log of infinity we obviously can't plot. So I've clipped that portion of that axis, and what we can see is as closer we reach to this minus 1 and the omega equals to 4 point, it is blowing up, it is going to infinity. So here this is how much frequency, this is omega equals to 1. Okay, and somewhere here, like this is another decade, this will be 10 raised to power 1 again. So around somewhere here, okay, like this is blowing up. So obviously I won't be able to show this in a 2D, like 2D space. This is iPad is 2D and this plot is 3D, so it will be difficult for me to see like explain everything, but I hope you get the point, right? Around this 2 points, okay, here both of the things are varying in 3D Bode plot, 3D plot of magnitude, sigma and my omega is varying, and here I can observe that yes, like if I plot it in the MATLAB, it is blowing up, it is blowing up. So in 2D plot we don't see any infinite gain because it is obviously not possible. Like we only plot for positive real frequencies in Bode plot, 2D Bode plot. But in 3D magnitude plot, I can see, because here another parameter is coming up, the sigma part also, sigma part also. Okay, so yeah, this is one thing. Like this sigma also you can say imaginary frequency, that also you can say, because omega equals to something imaginary is sigma itself, because like s equals to sigma plus j omega. Now if your omega is j5, omega is j5, then it will become what in this equation, sigma minus 5. So obviously it is sigma, like it is something like a sigma itself. So yeah, that is what I was trying to explain here, if your frequency is also imaginary. So yeah, this is the plot for this. Now if you want to see like the projection of the Bode plot, so the Bode plot is only this part, right, where my sigma is 0 at this particular point, where my sigma is 0. If sigma further reduces, we can see that at this particular frequency this is blowing up, but this is behind this, okay, behind this is not the, we just see the projection in front, this line we see, as we saw here, right? This is the line we saw, but behind this, as the sigma is reducing, the magnitude is increasing. So at this particular point it is blowing up. So obviously this is the confusion I got from few students, and also I was planning to explain this, but I couldn't get the time for all this. So this is the Bode plot and this is the 3D magnitude plot. So what is the Bode plot? Bode plot is basically the projection along the sigma equals to 0 axis and for positive frequency. So here this is the one key point I want to say, is that in Bode plot we only plot for positive frequencies. Basically the projection along sigma equals to 0 and omega greater than 0. Okay, these are the two things. So like, or you can say sigma equals to 0 and omega equals to 0, like these are the two conditions. Okay, so that is what we do in the Bode plot. So if in interview, like the interview may like try to confuse you with these things, so yeah, just have a basic knowledge of this, nothing too much in deep details you don't know. Okay, so like yeah, that is what I tried to explain in this lecture. I think this lecture was already gone long. I didn't want it to go that much long, just to try to explain a bit short concept, but that's fine. So yeah, I hope you like this video. Any more content you want, any more like topics you want, you can put it down in the comments. I don't have much time right now. I will try to bring content slowly. Just put it down in the comments whatever questions, whatever things you want, and obviously to hit the like button if you like the concept and all those things. And I will see you in the next video. Thank you for watching.